Hello everyone, welcome to my presentation. I will present our new research about cavitation evaluation for a ducted controllable pitch propeller, and it is equipped for a large trailing suction hopper dredge. I will introduce this paper in 5 parts. First, it is instruction, and then it is about the mathematical model. Finally, the open water and the cavitation performance are calculated. The conclusions are given then. The research on propeller cavitation has always been a hot topic. At present, there are cavitation experimental measurements and numerical simulation to study propeller cavitation. In terms of experimental measurements, research can analyze high-resolution cavitation images captured by high-speed cameras. In recent years, some researchers have turned their research direction to the hydromatic performance of ducted propellers. In view of this paper has done the following work. Based on the cavitation model, the propeller is simulated with unsteady conditions, and the numerical simulation method of the cavitation performance of the ducted propeller is established. According to the different pitch angles of the propeller, the cavitation performance was analyzed, and the occurrence range of cavitation was summarized. Then this paper analyzes the ducted design scheme and compared with the relevant regulations, and provide the issues that should be paid attention to when designing this type of ducted propellers. The specific research objects of the paper is the 4-blade CPP of a large trailing suction ship. When performing numerical simulations, the scaling ratio is used as 25. The cross-section shape of the new duct is an airfoil, and the geometric parameters are shown. In the middle of the inner wall of the duct is a stainless steel ring, which is welded with carbon steel at both ends to form a complete duct. The gap between the inner wall of the duct and the propeller is 25 mm or 0.01 R. In the numerical simulation, the cavitation flow is treated as a two-phase flow containing liquid and gas, which can be solved by the modified Lorentz equation. Use ρm and μm to express the density and viscosity coefficients of the mixed flow. The modified continuity equation and the momentum equation are as follows. Among them, TRE is usually called the Reynolds stress term or the turbulence stress term. In order to close the equations, it is necessary to make some assumptions about the Reynolds stress term and establish a corresponding relationship, which is the turbulence model. In addition, ρm and μm are determined by the gas phase volume fraction defined as follows. Likewise, a transport equation for alpha needs to be supplemented to solve for the mass transfer between the liquid and gas phase of the cavitation model. The Schnell-Schaper cavitation model is based on the ready-plastic cap cavitation model, ignoring the effect of the bubble growth, acceleration, viscosity, and the surfactance. The results show that for most practical applications, it is not necessary to consider viscous and surface tension effects. Therefore, the Schnell-Schaper cavitation model was used in this study. The computational domain of the ducted propeller is shown. The computational domain is large enough to satisfy the far-field conditions, but as the domain increased, the amount of computation also increased. The computational domain is cylindrical with a diameter of AD. The distance between the entrance of the computational domain and the surface of the propeller is 5D, and the distance from the outlet to the surface of the propeller is 10D. The computational domain is divided into the rotating domain and the stationary domain, and the diameter of the rotating domain is 1.4D. In this study, the polyhedral meshing technique is used to divide the mesh. When dividing the mesh, different degrees of densification are performed on the rotating domain and the weak region, and the intersurface mesh parameters of the rotating domain and the static domain are set to the same to ensure a conformal mesh. Due to the large change in the curvature of the propeller blade edge, the leading edge, and the duct and the trailing edge, these areas are locally encrypted. 5 layers are used as the propeller blades and ducts in order to ensure that the calculation is right. When calculating the open water performance of the ducted propeller, advanced coefficients is changed by keeping the propeller speed unchanged and adjust the inflow speed. The propeller speed is set to 617 rpm. Respectively, this table shows that the numerical simulation results of the propeller open water performance and the research results of the influence of the grid number change on open water performance. G2 takes G1 as a reference, G3 takes G2 as a reference, with the increase of the number of grids, except for the case of J equals to 0.7. The relative change range of the calculation results is within 2%. When J equals to 0.7, the relative change range is slightly larger. The main reason is that under the large advanced coefficient, KT and KQ, the absolute value of is relatively small, and the calculation result is slightly frustrated, which will lead to a relatively large error, but it does not exceed 4%, which is within the allowable range. Based on the above analysis, it can be seen that the G2 grids has reached the accuracy required for the calculation. Figure below shows the open water characteristic curve of the ducted propeller. When J equals to 0.1, the ducted thrust is basically equal to the blade thrust, so that the thrust of the propeller can be doubled. With the increase of the advanced coefficients, the thrust of the propeller is mainly derived from the blades, but the duct still produced positive thrust. In order to obtain the cavitation distribution on the blade surface and the inner wall of the duct more accuracy, the G2 grid is locally refined in a specific area. The cavitation number is an important parameter to decrease the cavitation of the propeller. First, the open water characteristic curve without cavitation is obtained by interpolation. The advanced coefficients J equals to 0.53 corresponding to the highest efficiency points, and the cavitation performance of the ducted propeller with different cavitation numbers under this advanced coefficient is calculated. Table below is the cavitation calculation conditions. And the figure below shows the curve of the hydromatic performance coefficient change with the cavitation number. It can be seen from the figure that when the number of cavitation is less than 1.5, the thrust coefficient, torque coefficient, and efficiency decrease significantly, and when the number of cavitation number is 0.5, the efficiency decrease. It can be seen that the cavitation seriously affected the propeller efficiency. In addition, when the number of cavitation is 0.5, the thrust coefficient of the duct becomes negative, which adversely affects the thrust of the entire ducted propeller. According to the parametric of the actual ship's self-propulsion, propeller and dredging conditions, and based on the similarity law, the calculation conditions on the model scale are studied. The following two figures shows the distribution of cavitation at different pitch angle under the self-propeller and the dredging condition. It can be seen from observing that the cavitation in the dredging condition is more serious than that in the self-propeller condition. The range is also wider, and the pitch angle increased. The cavitation on the duct will become more serious. Observing the gas phase volume fraction distribution map on the duct, it can be found that in the case of dredging condition, the worst area of the cavitation on the duct is just at the welding seam of the inner wall of the duct. And in other cases, the cavitation on the duct basically occurs on the inner wall of the middle ring. For the new duct propeller, corresponding to the actual working conditions, the cavitation conditions of the blade and the inner wall of the duct are calculated. Compared with the cavitation conditions of the original designed ducted propeller at the same position, the result is shown in the following figure. Observing the distribution of cavitation on different ducted propeller blades and ducts in the self-propeller and dredging conditions, it can be seen that the cavitation in the dredging condition is more serious than that in self-propeller conditions, and distribution range is also wider. The cavitation on the original design blades and on the duct will become serious, and the cavitation will develop more backwards from the leading edge, both for self-propeller conditions and dredging conditions. Observing the gas phase volume fraction distribution map on the duct, it can be found that the area with the strongest cavitation on the duct is just on the inner wall of the middle ring of the duct. Then generation and collapse of this bottle seriously affect the inner wall of the middle ring, which lead to the loss of the thrust conduced by the duct. The inner wall of the middle ring may fall off and damage the propeller. By adding stainless steel ring belt, the generation and cavitation on the inner wall can be suppressed, thereby improve the anti-cavitation ability. From this, we can draw 4 conclusions. Point 1. Numerous simulations of the open water hydromatic performance and cavitation characteristics of the duct CVP of a large suction ship show the feasibility of the numerous simulation method used in this paper, which can well predict the cavitation phenomenon of the propeller, which is the numerous simulation of the cavitation flow field of the duct propeller in the future, provide some reference of opinions. Under the model scale, when the rotational ring speed is 617 rpm and the advanced coefficient is 0.53, the hydromatic performance of the ducted propeller basically does not change much when the number of cavitation number is greater than 2. After, with the further decrease of the number of cavitation number, the hydromatic performance declines rapidly. This is because when the number of cavitation number is greater than 2, the cavitation of the duct propeller is not serious and is only distributed at the tip of the blade. The dynamic coefficient drops rapidly. Cavitation first appeared at the tip of the blade near the trailing edge. As the number of the cavitation decreased, the cavitation region separate to the root of the blade and then extend to the entire suction surface. Point 3. In the actual self-propeller and dredging condition, with the increase of the pitch angle, the cavitation on the blade and the duct will become serious, and the cavitation will gradually transfer from the leading edge to the trailing edge. Point 4. Under all the self-calculation conditions in this paper, the cavitation on the duct basically occurs in the inner wall area of the middle ring. The length of the inner wall of the middle ring should not only meet the strength requirements, but also consider the range of cavitation. By adding a stainless steel ring of the inner wall of the middle ring, the generation of cavitation on the inner wall of the middle ring, newly designed ducted propeller can be suppressed, thereby improve the anti-cavitation ability. Thank you all.